Start the class with this much participants. Only 30% participants I think have joined. 30 to 35% participants. So let me start the screen share. Okay, so we'll start today the bipolar junction transistor. So as I told in the last class, so we'll discuss today power BJT. Okay, so as you have already studied the bipolar junction transistor in your electronics class, so far I think that you have already studied it. But that bipolar transistor which we have studied, that is for different purpose. That is for generally amplification. But here in the power electronics, we will use the bipolar junction transistor for switching purpose. Hmm. so, so therefore, so as you have seen in case of diode also, that the structure of the power diode compared to the signal diode is little bit different. So here also the structure is a little different. So we generally prefer the vertical structure. Now vertical structure is preferred basically because it maximizes the cross sectional area, because the cross sectional area is the most important part for this power carrying capability. Okay, and also it minimizes the on-state resistance. So therefore, we generally use the vertical structure. So in diode also, you have seen that we use the vertical structure for power diode as well. Now here uh, in the BJT, you know there are two types of BJT. So first one is NPN and PNP. Now, the NPN transistor is preferred over this PNP transistor because the main carrier in NPN transistor is the electron, and electron has much higher mobility than the hole. So therefore, this NPN transistor is preferred. Okay, for this power applications, because the mobility, so electron is higher than the hole. Okay, so that is the reason for which we prefer the electron. So therefore, we generally we select the NPN transistor for these power applications. Now let me discuss the basic structure power transistor, the device structure. So as we have already seen in case of in case of power diode also. So let us draw the structure, then I will explain this. So here you have the N class, because I am discussing only the NPN transistor. So this is the N class, and here you have the base. Okay, and then it is equally halved. So this is your base, and the base is formed by only P, and this is N minus N plus. So this type of structure we use for NPN power transistor. This is the emitter, and this is the collector. and that is the base. So this is called the vertical structure. Now this thickness is kept around 10 micrometer. This thickness is kept around 5 to 20 micrometer. This thickness is kept around 50 to 200 micrometer, and this thickness is kept around 250 micrometer. Okay, and you already know the concentrations of N plus, P, N minus, and N plus substrates. So can you tell me what is the concentration of N minus substrate? Can anybody tell me what is the concentration of N minus substrate?
10 to the power minus 19.
What is the unit? Not minus. It is not minus.
Plus
Okay.
4.
Okay. So 10
20
to
on
the
10.
minus how much?
Sorry,
19.
minus 10 to the power 14 per centimeter.
I'm not getting 10 to the power minus or plus
14
14
plus.
Plus 19
plus 19.
in N plus and plus
N plus it is
14
plus
in N.
19. And what is the unit?
N minus is 10 to the power 14 per centimeter cube. Per centimeter.
Per centimeter cube.
Okay. So it is per centimeter
N
cube.
plus is 10 to the
So N
and
plus
19
also it
centimeter
is
cube. Yes.
10 to the power 19 centimeter cube. So impurity density. And what is the impurity density at P? P substrate?
So that is also 10 to the 19.
No, that is
I
16.
think.
16 plus.
Okay. It's different.
That is 10 to the power 16 per centimeter cube. Okay, so this is the structure and the symbols we use. So you have seen that the base is quite thin compared to this emitter. Sorry, compared to this collector. Okay, so collector region is quite large, and the base region is quite small and quite thin. Now the symbol which we use for NPN transistor, that is that you have already you know that what is the symbol used for this NPN. So how do we write this NPN? So what is this left one? This is called the base. Okay. Now if we use the arrow in this side, then what will be the collector and what will be the emitter? What is this one? What is the
So
top
the
one?
arrow one is the emitter.
The arrow
Collector
arrow one will be the
is
emitter,
emitter.
and this one is collector, isn't it? So that you have you know from your previous knowledge. So this is the representation of NPN transistor. What is PNP transistor? What we use for this PNP transistor? So for this PNP transistor, we use the symbol.
Arrowhead in
Hmm?
The arrow will be inward towards inward.
Arrow
Pro-
will be
in
opposite.
inward.
Arrow will be inward. Okay. And what is the emitter here? Base is same. Which is the emitter?
Emitter will be the one without the arrow.
Hmm?
Upper half.
So this is the emitter, isn't it? And this is the collector. So this is the symbols which we use for NPN and PNP transistor. Now, how do you bias this transistor? By external DC sources. Okay, so that we should know. Now the biasing is quite simple. We have to use two sources. We have to use the base emitter bias as well as the collector emitter bias. So if we have this, then this is C, this is B, this is emitter. Then which will be at higher potential between the C and E? Between C and E, which will be at higher potential? Can you tell me? And between B and E, which will be at higher potential? Anybody?
B is lower potential.
B it has higher potential.
Okay.
B is lower potential.
Uh, B is a higher potential with
NPN.
respect to the emitter. Okay.
C is at lower
And
potential
that
with
is
respect
called
to
the BB. And here we are, it is also called the, okay, so here we use the VCC. So that is collector is always at higher potential in NPN transistor. Okay, and this is the, you can say the load resistance. And this is the bias for this collector. And this is the positive direction of this collector current IC. So this is how we bias NPN transistor, and for PNP transistor it is similar. So here also it is. Okay. So this is the emitter here, this is the base, and this is the collector as we have already shown in the previous diagram, and here the positive current direction is emitter to collector. So this is your IC, and that is the load resistance RL. So this is how we bias the NPN and PNP transistors. Okay, so let's consider the characteristics of this PNP and okay, so we'll now onwards we'll consider only the NPN transistor for our discussion. Okay, so let's start the characteristics. So one of the very important characteristics is transfer characteristics. Okay, so transfer characteristics is basically the plot between the IB, and that means the base current, and VCE, collector emitter voltage. Okay, now if we look back to this NPN transistor, so this NPN transistor, if we look back, now you know how it works. How does it work? So any idea? We have two junctions. Okay, so one is called the base emitter junction, and another is the collector base junction. If you have already studied this in your electronics class, so you should have a little idea on BJT.
So can you repeat the question?
Uh,
Sir, can you repeat the question?
I'm asking that can you tell me how does it work? How does it work? The NPN transistor with the proper bias. Okay, so I think you have forgot something.
So first the current will increase when VC increases, and then when it reaches saturation, then the current will become constant. And if VC increases, then also the current remains
No,
constant.
when which current will increase and how the current will increase?
But so IE will increase. IE will
I have
increase.
not drawn here. I have not drawn yet. I have drawn only IC, collector current.
Yes, sir. IE will increase and IB is constant due to the bias. So that is why IE is equal to IB plus IC. So as IE increases, IC also increases.
Okay, so what is the mechanism? Why the IE increases? Okay, so you can think this device is like a gate. Gate means have you seen a log gate in any dam? Okay, so in a log gate in any dam, so you have one uh, part of the dam at the water is at a higher potential. So another another part of the dam at its lower potential. But until the log gate is closed, no water can flow. Okay, so here also the thing is similar. So though you have a the bias between this collector emitter, so current can flow, but current can't flow until the base emitter junction is forward biased. Okay, so that means this base emitter junction or the base current is just like the log gate. If it opens, then the water will start flowing. Correct. So the base emitter junction should be forward biased and the base current should flow with its sufficient value. So that means the base current determines that how much current will flow in that collector emitter path. Can sometimes you also define the current gain like that, isn't it? Some gain you have studied in electronics, that beta, alpha, etc. Isn't it? So can you tell me what is the beta gain?
So current gain in a transistor.
What is that?
IC by output current by
IC
input
by
current.
IB.
IC by IB.
IC by IB. Okay, so how much value generally we get for this beta?
Sir, 100 to
Hmm?
200.
100. Okay. So that means this the base current required is very small. The very small base current is sufficient to open the log gate, and then the sufficient current will flow in the collector emitter path. So therefore, there are different regions for this transistor. We call it as a cutoff region, active region, and saturation region. Okay, so therefore, the plot I have drawn here. Here you see it is a base current versus VCE. Okay, now the VCE value, that voltage, when that will be the VCE voltage will be the maximum, when this is closed, that the log gate is closed and the log gate is open. কখন VCE ভোল্টেজটা ম্যাক্সিমাম হবে? যখন পাথটা ওপেন আছে, মানে collector emitter path is open or collector emitter path is closed?
The closed.
Okay,
was open.
you just try to understand. If it is closed, then no current is flowing through this collector emitter. So that means the total voltage drop will be across the collector emitter, and that is VCC, isn't it? So that means when the base current is very small, it is not sufficient to open the gate, open the lock gate, and there is no current flowing through the collector emitter path. That time the total collector voltage will be across, because through the through the RL there is no drop because there is no current. Then the total VCC voltage will be appeared across this VCE. Have you understood? বুঝতে পারছো এই পয়েন্টটা? If I don't open the gate and if there is no current flowing through this collector emitter path, then the whole VCC voltage will be appeared across VCE. But if
Yes,
there is,
yes.
are you getting?
Yes, yes. Yes, yes.
Okay, so after current flowing, then there will be some drop in RL, na? Are you getting this?
Sir, RL is load resistance.
RL is load resistance. This load resistance. So this is plus, this is minus. If there is no voltage drop, then only VCC will be appeared across VCE. And if there is some current and current in this direction, so this will be the polarity, and these two polarities are opposite. So that will appear across this VCE as per this KVL, isn't it? You have other side, you have VCE only, na? So this voltage is VCE.
Yes.
So if there is no current, then there will be no drop. No drop here, no IL RL drop or IC RL drop here. Okay, so that is the maximum voltage which will appear across the VCE. So it's simple, by KVL only you can say that. So that means when the base current is very small, the gate is closed, there is no current in the collector emitter path, then we will get the maximum voltage, and that is VCC, the collector bias voltage. Okay, now once the lock gate starts opening, then will the current, the collector current starts flowing, and then there will be reduction in the voltage across this collector emitter junction, and this voltage will reduce like this. Okay, then what will happen? Then when the lock gate is fully open, okay, when the lock gate is fully open, then you cannot increase the flow further. You cannot increase the flow further because that is the maximum value you can get, maximum collector current you can get. Okay, and that is termed as the saturation. And there again the voltage will be constant, and that is called the VECE saturation. Okay, is that clear? Is this point clear? Now what is
Yes,
the
sir.
cutoff region here? So this portion is called the cutoff region. This portion is called the active region, and the rest is called the saturation region. So if I draw it 1, 2, and 3, so this one is called the cutoff region, when there is no collector current. Number 2 is called the active region, and that is the saturation. Now we operate the signal BJT, signal transistor, which we use for the electronics application that we have studied. We mostly concentrated in this active region. But when we are discussing the power electronics and we are discussing the switching using this power transistor, we are mainly concerned with this saturation region. Okay, so we deal with this saturation region for power electronics application, or sometimes the region just between this active and saturation region, which is also called the quasi saturation region. Okay, just the point very near to the saturation region, so this is called the quasi saturation region. So I will discuss this later, how we get this quasi saturation. So have you understood these characteristics? Any doubt?
No, sir.
Okay. Now we'll write down a few characteristics of BJT only for this information. And
Sir, cutoff region can also be used in power electronics.
cutoff
Cutoff region can also be used in power electronics.
cutoff region
And
means there is no
divided
current. Okay, so
into
that either saturation or cutoff, so that is called the switching. I didn't understand your query.
sir, in power electronics, can we use the cutoff region also?
Cutoff region means the device is switched off, so that you can use in any application. You can switch off your device. Okay, so that means in case of on-off controller, if your power electronics switch is being used for on-off controller, then either you can operate in this saturation, or you can operate in this cutoff region. Have you understood? Okay.
Yes, sir.
Now, if we want, I can also draw the voltage drop exactly. How do we get here? Okay, so for this active region, so this is your base, this is your collector, and this is your emitter junction. Sorry, emitter terminal. Okay. Now, for this active region, what are the polarities of VBE, VCB, and VCE? Can you tell me? What is the polarity of BE, which is positive, which is negative. Suppose this is your NPN transistor. Now I am interested in
So for
active
NPN,
region.
C will be positive and B.
No,
So for
in this
active
VB, first you
VB
tell me the VBE junction, because that is the driving.
B will be
positive.
B will be positive
E.
with respect to E.
E will be negative with respect to C and V will be positive.
Okay, so first let me write this one by one. So this is your VBE voltage, isn't it? Do you all agree this?
Yes.
Yes, sir.
Okay, so if you agree this, then what is the collector base junction? What is the collector base junction?
so it will be reversed
Collector will be negative.
with respect
Hmm?
positive. Collector will be positive with respect to
Okay, so the collector will be positive with respect to the
Collector will be
base.
positive, sir.
Okay, so that you should understand this. So this is the VCB voltage. Now what is the VCE voltage? VCE. You can now just apply your KVL for this. You can now just use your KVL for this. What is
Yes, sir.
VC?
Summation of both.
Summation of both. Correct. Now this is the active region. Now let us draw the saturation region. So these polarities are very important. Saturation region. Now you tell me the polarity of B and E.
so B will be plus and E will be minus.
So B will be plus and E will be minus, because the lock gate should be open always, both in active as well as saturation region. So it will be BBE. Now what about the other junction, BCB?
C will be minus, B will be plus.
Why?
So two junction is forward bias factor.
Which one?
So base collector, base emitter, দুটো junction is forward bias factor.
Base emitter and base emitter always
base
will be for.
saturation is a collector based on forward bias factor.
Correct. So that we get from this device characteristics. Though I have not discussed the device thing, but it should be the case. You just remember that for saturation region, both the junctions are forward biased, and therefore C is negative with respect to B. Now, if we now try to write the expression of VCE, what will be that? By using the KVL, simple KVL.
স্যার ভি সি বিটা একবার বলবেন, ওইটা মাইনাস আর সিটা বিটা পজিটিভ কেন?
What is this substrate? N, and this is P. Okay, so what he told that in saturation region, both the junction should be forward biased, isn't it? So suppose B base emitter junction is forward biased, therefore P side is positive, N side is negative. Now to make this collector base junction forward bias, the P side should be positive and C side, the N side should be negative, isn't it? So therefore this should be positive and this side should be negative. But now why in the saturation region both the junction gets forward biased? That if we want to understand that, we have to go for this device, how device operates, that we have discussed in case of diode. So that type of discussion we should have. Okay, বুঝতে পেরেছো? Now only you remember that for saturation region both the junctions are forward biased. In active region base emitter junctions are forward biased, but the collector bias base junction is reverse biased. And what is VCE then? By using KVL,
Sir, VBE minus VCB.
VBE minus
VCB.
VCB, correct. So this you just try to remember, this will be required in our later stages. Okay, now next I will discuss a few parameters, important parameters for BJT. Important parameters of BJT. Okay, so what are the important parameters for BJT? Because when you will go for any device selection means for a particular application, you want to select your device, you want to select the BJT. Now what are the things you should uh, think, what are the thing you should consider when we select a proper device or proper BJT for your particular application. Now, all these values, all these parameters are generally mentioned in the data sheet of that device. If we open the, so all the data sheets are freely available over internet. And if we open the data sheets are basically the PDF files. So if we open the data sheet, you'll get all these important parameters mentioned there. The first one is the maximum collector current and the instantaneous value for that. So it is called the instantaneous maximum permissible collector current. Instantaneous maximum permissible collector current. So that is the IC max. Okay, so that is the first important property. Then number 2, continuous. So continuous value of possible value of collector current. So have you understood this difference, the instantaneous value and the continuous value? One value that in steady state, the maximum value in the steady state BJT can carry, the collector of the BJT can carry. Another one is the some value in instantaneous transient condition a BJT collector of a BJT can carry. So that is the thing. Now, can you tell me which value should be higher for any BJT device?
I see.
Hmm? IC continuous or IC max?
IC max.
Why? কেন ওটা বড় হতে হবে?
So because in transient condition, current may be more higher than normal current. So
Okay, so transient condition, that means this current IC max that will appear for very small time. Okay, and generally the maximum permissible means what will be happen after that? The device will be burned or device will be damaged. Why the devices are damaged? Mainly due to either due to this production of heat or very high voltage gradient, isn't it? Now if for very small time this current will flow, okay, then the device should carry much higher value of this instantaneous current, isn't it? Because that is flowing for very small time, isn't it? Have you understood this point? So therefore the IC continuous current is less than this IC max always. Now the maximum forward voltage that can be applied within the collector and an emitter, okay, with base there is no connection in base, so therefore VCEO. Have you understood the voltage between the emitter collector and emitter with the base open? So we should write the maximum forward voltage can be applied between collector and emitter with open base. So that is called the VCEO. Now VCER the maximum voltage that can be applied across collector and emitter. Same. Collector and emitter with a resistance connected between base and emitter. Previously it was open, now okay. So this is the VCER. Now VCEX, that is also the first part, it's same, but here what is the difference? Difference is there will be some voltage, negative voltage, which will be connected between the base emitter. Okay, so the first part is similar, that means the maximum voltage that can be applied between collector and emitter with a negative polarity voltage, with a negative polarity voltage between base and emitter. Okay, so VCAX, then VCE sat, that you have already seen in the transfer characteristics. So VCE sat, so the voltage between the base and emitter, voltage between the base and emitter under saturation condition. The 7 one is that also you know the
Sir,
gain.
VC sat is the voltage between base and emitter.
Sorry,
Should not
no.
it be
Collector
collector and
and
emitter?
emitter. So all is collector and emitter only. Just a minute. It's not working. Collector and emitter. Okay. Now what is the gain beta? Beta is that already you have mentioned, that IC divided by IB. Okay, but it is defined only in active region. So these are the parameters, these are the important parameters. Other parameters are also there. Other electrical and mechanical parameters also mentioned in the data sheet, but these are the important parameter which is mentioned in the data sheet of a particular BJT device, and which will consider for selection of proper device for for a particular application. Okay, so you should remember this. Okay, do you have any question? Now we discuss a few VCE, that is VCE 0, VCE stat, sorry, VCE X, VCE 0, and what is the other VCER? What are the differences between them, and which value should be more and which value should be less? Okay, so if we so that means we are, which point we are discussing? 3, 4, 5, etc. Okay, so if we think of this VCE 0, VCEO or VCE 0, then the base should be open like this. The base is open, and this is called the VCE 0. Okay, now if I call it VCER, what will be the figure? Here we'll get the VCER only if there is a resistance connected between the base and the emitter, as mentioned in the specification. Okay, and VCEX, all are NPN transistor. VCEX, so it will be called VCEX only if there is a negative polarity voltage connected in the emitter, sorry, connected in the base and emitter, between the base and emitter. Okay, so these are the differences between these values of this VCE0, VCER, and VCEX. Now, can you tell me that between this VCER and VCE0 or VCEO, which value will be higher side? Hmm? Which value should be higher, VCER or VCE0?
VC 0.
VCE0 should be higher. Why?
Because in VCR we'll get the drop due to the resistance from E to D addition, which was not there in VC also.
No, no. That drop, that drop, which resistance? That resistance is connected here in that base emitter junction. So this is emitter, na?
VC
Now,
In
generally,
both the cases, base.
both the cases, and then how the, that is the, all the base current here will be due to the leakage, isn't it?
Hmm.
Isn't it? Base current, how the base current can flow if the base current, the base is open circuited? So only possibility is the leakage current. isn't it? Now, if some leakage current is there, now in case of VCER, this R will bypass the leakage current. Are you getting? Suppose due to some
So
thermally
both the
generated.
cases there will be no current.
Okay, so but ideally there will be no current. But as you know,
Okay,
due to the
ideally so there
temperature,
will.
ideally there will be no base current. So ideally all these VCE should be same. That you can say, because all these VCE should be the cutoff voltage, isn't it? So that means
Yes,
in all
yes,
these
yes,
cases,
yes.
your device is in cutoff region. That means all these cases of VCE0, VCER, VCEs all should be same. But that is not the case. So therefore they have mentioned differently in the data sheet. Na? So there is slight differences.
Okay, sir.
So due to the temperature change, if the temperature is higher, then the thermally generated carrier will be more and there will be more leakage current. So if some base current, base leakage current is there, okay, then what will be the case? The VCE will be less compared to the absolutely zero base current value, isn't it? Are you getting? Now that is the case for VCE 0. Now if we have resistance there, what will happen? The resistance will bypass that leakage current, and that leakage current will not flow through these junctions, and therefore the VCR will be more compared to this VCE0. VCER will be more compared to VCE0, because in the first figure there is no path to bypass the leakage current. Are you getting? The same case is also valid for the third case. Here also you are forcing the current to flow in this path, because you have already biased that. So that means here also you will get the VCEX will be more than the VCE0. Okay. So these are the very small differences between this VCR, VCX and VCO value. Okay. Now the next point which I'll discuss, the important characteristics of BJT. Important
Sir,
characteristics
can the VCR and VCX be compared?
compared, but that R value you can change, the this value also you can change, na. So therefore, if we want to
Yes.
compare, you have to take a definite value. Otherwise, what is the necessity of comparing these two? Are you getting? মানে তোমাকে এখানে একটা তাহলে ভ্যালু নিয়ে কম্পেয়ার করতে হবে।
Yes.
এরকম হতে পারে for certain value of R and certain value of this V or this V dash, whatever. Certain value of this R and certain value of this V dash, both these values are same. That means VCER and VCEX is same. Okay. Now, definitely when a data sheets are prepared, they take a certain value of R and certain value of this V prime. So, but that depends on the manufacturer, which value they take. Okay.
Okay.
So important characteristics of BJT now we'll discuss. The first one is lower voltage drop. So that already we discussed very earlier classes where we had discussed the in general the important characteristics of the power electronics devices. So here also these points are valid for BJT. So that is the first point is lower voltage drop between collector and emitter because that is the main path. Are you getting why we need this lower voltage drop between this collector and emitter? Suppose we have a resistance. Okay, now we want to control the power, that is P equals to I square R. This power we want to control. Our voltage is fixed. The fixed voltage, the power we want to control. So how can we control this? By switching on and off the voltage, isn't it? Are you getting? How can we control the power? If we control the, if we can control the R or the I, now R is fixed. Now I, how you can control? Because it's a DC. It's a DC voltage. So how you can control the I? If the switch is on, if the switch is on, then the current will be what? Current will be VDC by R. Okay. And if the switch is off, the current will be 0. Okay, so that means the current will be either 0 and I. So this current either will be 0 or VDC by R. So this is how you can control the average value of the current. And your power depends on the average value of the current. So that is how you can control the power. So this is how you are periodically you are switching on and off the power supply. So this is how your average voltage will be changed and you will get the variable power dissipated across the resistance. Okay, now instead of this switch, manual switch, what we are doing here, we are using a BJT. We are using a BJT like this. Now this is the main path. This collector emitter is the main path. Okay, so the voltage drop in this main path should be as minimum as possible because you are controlling the resistance drop. Now if there is a huge voltage drop or power loss in the device, in the controller itself, controlling device itself, so that is not recommended, isn't it? So therefore the voltage drop in the collector emitter path should be as small as possible. So therefore the first point we have written, the lower voltage drop between the collector and emitter. Okay, have you got this point? Emitter in the, because we are operating when we are operating the power electronics devices, we are operating as saturation region. Number 2, high current carrying capability. Okay. So how it can be high current carrying capability? How it can have high current carrying capability? The device. How can we increase that? Any idea?
So by using the cross-sectional area and using vertical
Correct.
configuration.
By increasing the cross-sectional area. That means the size of the device will be more. Or you can use a more doping. The doping density you have to increase. Isn't
Sir,
it?
increasing current carrying element,
Current carrying element means?
electron, more doping means more impurity.
So that that only I am telling, na? You have to increase the doping. You have to increase the
sir.
doping density. And that is one point. Another point, what he has pointed out, the cross-sectional area. That will increase the size of the device. Okay, so that you have understood. Now, the third point is the negative base drive is used. Used to reduce. So that this point I will discuss later, because for that we need a little discussion on device. Turn off time of BJT and increase in, and you know that if time is reduced, then we can increase the switching frequency. My device is getting hanged today. Frequency. So number 4, the safe operating area is called SOA. Safe operating area, or SOA, is bounded. So that also you don't understand this term SOA. When you discuss the device, you will understand better.
স্যার অ্যাক্টিভ রিজন আর সেফ অপারেটিং এরিয়া কি একই?
অ্যাক্টিভ রিজন সেভ অপারেটিং রিজন একই নয়। সেভ অপারেটিং রিজনটা আছে পাওয়ার কনসিডারেশন ধরে। সেভ অপারেটিং রিজনটা হয় পাওয়ার কনসিডারেশন ধরে। সেটা আমি পরে পড়াবো।
মানে স্যার জেডিডি আর ও আচ্ছা আচ্ছা ঠিক আছে ঠিক আছে, পাওয়ারের জন্য আচ্ছা ঠিক আছে ঠিক আছে।
Is bounded by the second breakdown. So you just write down these points, I will discuss later. The switching frequency of BJT. Okay. BJT much higher, not much higher. It is uh, around you can say 10 to 20 kilohertz. The gain is poor, in the order of 10 to 15. So these are the characteristics, important characteristics of uh, power BJT, which we use for our power electronics applications. Okay, so these 2 points I have not discussed yet. So you just remind me if I miss these two terms. So this is one term and this is one term. So these are very important thing. Okay, so these are the two terms you should understand more clearly. So anyway, if we have any other doubt, you can ask me.
Sir, at the beginning of this class, you said that while using vertical configuration, the on-state resistance get de-
No, not
decreases. And how is it?
no vertical. What I told? What I told?
Due to using vertical configuration, on-state resistance
No, on-state resistance is
decreases.
not reduced for that. Actually, by using the vertical structure, what we can do, we can maximize the cross-sectional area. Okay, and we can reduce the thickness. So that maximization of cross-sectional area will reduce the resistance because resistance is inversely proportional to the cross-sectional area. Okay, so that is not the directly
Okay.
related, but the resistance is indirectly related. If I use the vertical structure, there is a provision of increasing the cross-sectional area, and if we can increase the cross-sectional area, then the resistance will be reduced because the resistance is inversely proportional to the cross-sectional area.
Okay, sir.
Okay. Any other doubt? Any more doubt? Okay, so if you don't have any other doubt, so I will.
স্যার
Huh.
স্যার বলছি যে সাউন্ডটা কমাও না স্যার বলছি যে আজকে রেকর্ডেড ক্লাসটা একবার দেবেন স্যার কারণ প্রচুরবার আমাদের এখানে কি বলে ওই নেটওয়ার্ক ড্রপ হয়েছে
দেবো তো।
সামনের দিকে
Send
অনেক
the-
কিছু বলেছেন যদি আজকে রেকর্ডেড ক্লাসটা দেন খুব ভালো হয় স্যার
hmm.
Sir, could you repeat why VCR greater than VCO, please? One time.
VCR, which one?
এই যে স্যার
VCR
VCR কেন VCO থেকে
কেন VCR টা
greater than
VC
VCO এটা স্যার একবার
হ্যাঁ
যে রিপিট
হ্যাঁ বললাম তো
হ্যাঁ
হ্যাঁ
বড়
বলছি if the actually the VCO uh, depends on the leakage
Yes.
current value which enters from the base to emitter junction. Okay, and why it can happen because of this thermally generated carrier due to the elevated temperature, isn't it? Now if we have another path like in the second figure, another path is through the resistance, then the additional additional carrier which is generated due to the elevated temperature can be bypassed through the resistance, and that will not flow through the junction, base emitter junction. Directly it will
Okay.
bypass through this resistance and it will come from base to emitter. It will not flow through the base emitter junction. And if it doesn't flow through the
Okay.
base emitter junction, then the VCE voltage drop, will not drop, isn't it?
Mm-hmm.
বুঝতে পেরেছো? So therefore VCR is
Yes.
little bit higher compared to VCE0.
Oh, acha, sir. Yes, sir. Has understood.
Okay.
Okay.
So I am stopping the share and I will take the attendance, but some of you have not. Actually, what I told in the last class, that when you will enter to the class, you should rename yourself in proper format. But nobody maintained the proper format except few, like Bikash, Somnath Pal, Arijit Pal. So Somnath Pal, Arijit Pal, Hasibur Rahman, Amrita Dotto. So these peoples only maintain the proper format. So that means I ask you to rename like the first last four digit will come first, then your name and surname. Okay, so you should rename yourself like that. Somebody has not renamed themselves at all, like Ankush Ghosh, Sheikh Mohammad Iqbal, Tina Bishas. Okay, so they haven't renamed themselves. So then it is difficult for me to take the attendance. So what I do generally, I take the snapshot and it takes a lot of time. I take the snapshots and saved. Then I take the attendance in due course. So today also I have to do like that only because most of you have not followed the instructions. Okay, so let me take the snapshots. You just wait for some time. But one thing I want to tell you, that the attendance is getting poor day by day. It should not be the case. Then we have to take a different measure. I will talk to our departmental head so that because that is a general report for your class particularly for this third year classes. So we should take a different measure to increase this attendance. Okay, so you just wait. Let me take some snapshot of your class attendance. Then I will end today's class. And I haven't shared the videos of last few lectures. And you also haven't mentioned that. I think you don't need those. So therefore you haven't mentioned this, isn't it?
স্যার না না ওগুলো দিলে খুব ভালো হয়
But nobody mentioned, and I okay. So two another people are waiting. I don't know, Ankit Jaiswal and Ali Hamjan. They was there in the class before, but how they missed, I don't know. Okay, so anyway, so let me end today's class. Thank you.